Hi, we're Team Termodinamicos, and today we're going to explain the activity 4. Well, first for the code, we need to clear all the variables to be able to, have like a new set of variables. Then we defined the initial conditions, the volume, the moles. We calculated the moles with this formula. Then the pressure for each point on the Stirling engine cycle. Then for the first line of the Stirling engine cycle, we did like a list of numbers from our initial volume to the final volume, and we use this like list of numbers in between them to be able to get the pressure. Then for the isocoric lines, we needed to make like a list of also values of the temperature from the cold one to the hot one, and then did the same for the pressure. Just that for this one, we use the actual values of pressure, and with these values, we obtain the volume. Then for the other isothermal, we did again the volume from B3 to B4, where B3 is equal to the volume 2 and B4 is equal to the volume 1. And we obtain the pressure for each of them. And finally, we did the same for the last isocoric line. Also did a list of the temperature from the hot one to the cold one, and the pressure with the values obtained to be able to obtain the volume from each point. And yeah, that's all.
Um, well, and as for the values we replaced, I will basically go, I think I'm gonna go first with the volumes, where we replace B1, which is when the system is at its expanded state, basically taking that part of the chamber. Then B2 would be basically the complete chamber plus the connection tube minus their displacers. That's why that's two additions and one subtraction, which in this case the subtraction would be the marbles, as those work as their displacers. Something interesting is that B3 equals B2 because those are isocoric processes, as well as B4, which equals B1 because those should be our isothermal process. Then I'm gonna go and explain some of the pressures. Firstly, as for our initial pressure, that's just the atmospheric pressure, I think. And then for point A, which is P1, that we basically just cleared out the formula of an ideal gas to obtain the number of moles. And yes, we basically did that for P2, P3, and P4, just replacing the temperatures, the values of the temperature to get either higher or smaller values.
And if we plot this code, we are gonna be obtaining a PV diagram. Let's just wait until it performs the whole plot. So we obtain this PV diagram, and we can see that it has two isothermal and two isocoric processes. At a naked eye, we can see that all of these are straight lines, but if we zoom and take a better look, it has a little curvature from here, from the point A to the point B. But what does this mean? So at first, an isothermal process is happening. This means that the air is expanding. Then our first isocoric process happens, and well, here our volume is constant, but our pressure decreases. Then from our point C to our point D, another isothermal process is happening, and this is where our syringe, in this case, is compressing. And finally, the system starts again, And from D to A, the process starts heating up again and doing the whole process. So it's a cyclic process. So this is what it means.
So next, it is important to mention that as the ideal gas law reveals an inverse relationship between pressure and volume at constant temperature, the line of the isothermal processes should result in a hyperbolic curve when plotted. However, when the volume range is small, the changes in pressure are minimal, causing the curve to appear almost like a straight line, as Camila said. And this is because with the small volume changes, the variation in pressure is too subtle to create a noticeable curve, and it visually approximates like this straight line that we can see in color red and yellow. And on the other hand, when the volume range is expanded, the pressure changes and become more significant, and the curvature of the graph becomes more visible. So a larger volume range allows for a more noticeable drop of pressure as the volume increases, but we couldn't change them since our data is based on the experimental part.
And this is how we can demonstrate the functionality of our Stirling machine using MATLAB. With this PV diagram and with the code made, we can conclude that a cyclic process is happening when we are experimenting with Stirling machines.